group, it's Mrs. Schaus, back to talk with you some more about section 2.6. Our next learning target, 2.4, is to be able to identify types of symmetry. We should be able to use a graph to determine types of symmetry, but there are also some algebraic tests that can be used. If you're talking about a function, f, and you're trying to test the function for symmetry using these algebraic means, then we would say that the function is symmetric with respect to the y-axis, or we call that an even function, if when we calculate f of the opposite of x, we find that it equals the actual function that we started with. We're going to test it out in a minute, and you'll be able to see what I'm referencing there. And also, if we take that function and we determine that it is symmetric with respect to the origin, we would call that odd. And we perform that test by, again, looking at f of the opposite of x, but what we discover is that it equals the opposite of the entire function f of x. Functions certainly can be even, odd, or neither one. Relations could be, both. Okay, but we're not studying relations right now. We're only studying functions. So the question is, are these even, odd, or neither? Remember that our test starts out by taking a look at, well, I guess I don't want to use f of x. Maybe I'll use g of x here since that's the name of our function. But we want to start out by taking g of the opposite of x to see what we get. That means I'm going to put the opposite of x everywhere in the function here that I see x. And then I'm going to try to simplify or clean it up. So if I have a negative x times another negative x, a third negative x, and then times a fourth negative x, 4 negatives are going to end up giving me a positive, right? So this expression will actually just go right back to being 3x to the fourth power. And similarly here, if I have a negative and I square, negative times another negative, this piece just becomes positive x squared, but I am multiplying it by -2. So it simplifies to look like that. Oh, g of the opposite of x looks exactly like the original that I started with. G of the opposite of x equals g of x. And remember, that meant that the function was even, or in other words, symmetric with respect to the y-axis. All right, let's take a look at another one. Here's our h of x. If I begin my test with looking at h of the opposite of x, plugging in the opposite of x everywhere that I see x. Now when I go to clean things up, 3 factors that are negative will leave me with a negative result. So this piece really becomes -7x cubed. And here when I have the negative x and I square, this piece becomes just a positive x squared. But again, I'm multiplying by -4, so it's -4x squared. Now, I want to go back. Does h of the opposite of x equal exactly the same h of x we started with? The answer is no. So h of the opposite of x does not equal h of x. That tells me that it's not even, right? And how about h of the opposite of x? Sort of a question here, does it equal the opposite of h of x? Well, the opposite of h of x means that every single term here should be the opposite. So I do have the -7x cubed, but I don't have a positive 4x squared. So this is also not equal. The answer to this one is neither. And while I didn't provide an example of one that was odd, just as I had mentioned, if I had ended up with the opposite sign here as well, I would have said these two were equal and that the function was odd. We're going to talk a little bit more about even and odd functions in class, just to kind of clarify a few things. All right, let's talk now about Learning Target 2.5, still section 2.6, but where we're asked to write an equation of a function from its graph. And really, we're going to look at graphs or also other information being given about the graph. Okay. All right, so we're going to take a look at a few graphs here and see if we can write the parent function and then the new function. So this function we should recognize as being our absolute value function. So I'm going to call, here, let's write, let f of x equal the parent function. So for each of these, when I write f of x, I'm talking about the parent function. And then now what we want to write is our new function. I'll call this one g of x. So we have to kind of look to see what has changed about the function. Well, this function is no longer, no longer does it have its vertex at the origin. It's been shifted in two directions. It's been shifted to the right 2 units, and it's been shifted 1, 2, 3, 4 upward. So I'm going to need to change this function to reflect that, change the function's equation to reflect that. I know that no dilation has occurred because I still have a slope of 1 here and of -1 here. All right, remember that in a horizontal sense, that since x is the counterintuitive variable here, the 2 units to the right might make us think plus, but it's really minus, a subtraction from the x. So x minus 2 to represent that shift 2 units to the right. And then now shifting up 4 units, that happens after the parent function is applied, so after the absolute values, and it's in the direction we would typically think. So up 4 makes us think plus 4. There is our new function, g of x, the absolute value of x minus 2, and then plus 4, that represents that graph. All right, let's take a look at this next function, which again has a parent function, the square root of x. And how has that graph been changed? Well, in a shifting sense, I know that it normally starts here and works upward, so I can tell that it has been shifted back 5 units, or in other words, 5 units to the left, so I'll have to account for that. As far as the dilation is concerned, I know that this graph of the parent function, normally when it starts here, then it also passes through the point 1, 1, and it passes through the point 4, 2. So from here, I'm going to go, over 1, up 1. Yep, it's there. I'm going to come over 1, 2, 3, 4 units and up 2. Yep, it passes through that point. So this hasn't been dilated in any way. So now I want to write an equation for that function. Maybe I'll call this one h of x. And all I have to do is adjust for that shift 5 units to the left, which means to the x, I'm going to add 5. All right, let's continue on with a couple more. I've got a couple of parabolas to look at here. This first parabola, instead of the origin being the point of the vertex, it has now been shifted down 3. So I want to reflect that shift down 3 units. As far as a dilation is concerned, I want to look at from the vertex, do I travel over 1, up 1, over 1, up 3? Yes, I do. So it has not been dilated. So I'm going to go ahead and say the parent function is f of x equals x squared. In our new function, I'll go back to using g of x again. I'll call this g of x. That equals, with a shift down 3 units, remember that doesn't happen to the x when it's vertical. It happens after the parent function of a squaring is applied in this case. So minus 3 right there. All right, let's take a look at another parabola. So we know that this parent function is going to be the same. It's f of x equals x squared. But what has happened to this function? I do still see the vertex at the origin, so it's not being shifted right or left or up or down. But it does open downward, which tells me that a reflection has occurred. And the reflection is representative of something that was reflected through the x-axis. So that means I need the opposite y, or the opposite of the whole function. All right, but in addition to that, I also noticed that from the vertex, I'm not using my normal pattern. It's not over 1, down 1, over 1, down 3. I'm actually traveling over 1, down 2, over 1, down 1, 2, 3, 4, 5, 6. So I'm traveling vertically twice the distance that I normally would. So that tells me not only is there a reflection, but there is a dilation. And that dilation is a vertical stretch by a factor of 2. So now when I go to write my new function, I'll call it h of x, I'm going to take that x squared, and both of these, the reflection and the dilation, are happening in regards to the y. So I need to multiply by 2 for the stretch, but I need to take the opposite for the reflection. So I'm really just multiplying the x squared by a negative 2. Okay. I want us additionally to be able to write equations for functions if they tell us something about the graph. So you're asked to write the equation for an absolute value function. All right, that means our parent function f of x equals the absolute value of x. When it has been reflected over the y-axis and shifted right 3 units. Right, when I think about the reflecting over the y-axis, reflect over the y-axis, that's changing the sign of the x. So my new function inside, that before this parent function is applied, I'm going to take the opposite of my x. But this also says that the graph has been shifted 3 units to the right. Well, I need to think about taking that x first and doing the adding or subtracting to it. So if I'm shifting 3 units to the right, remember that since x is our counterintuitive variable, this should really be a minus 3. So inside my absolute value, I've really got the opposite of the quantity, x minus 3. Some of you might also change that then to say the absolute value of negative x plus 3. I wouldn't want you to confuse that plus 3 as being a shift to the left, however. So I really kind of like it written in this form. You certainly could check that one out with your graphing calculator to make sure it looks to you like it's been shifted 3 units to the right. All right, for the next one, our parent function is y equals x squared. They're directly telling us. I don't even really need to rewrite that, do I? It has been shifted 2 units left, 4 units down, and there's been a vertical shrink by a factor of 1/4. Vertical shrink by a factor of 1/4. Well, we know that vertical dilations mean that we're multiplying the entire function by this number, and we need to account for these shifts. So let me write down y equals 1/4 times, and now because there is a shift left, something is going to get done to the x before the squaring, and because there's a shift down, something's going to happen after the squaring. Okay, so for the horizontal, remember that we sort of think counterintuitively, so 2 units left instead of minus 2 is really plus 2, but 4 units down is, in fact, a minus 4. All right, I hope this helps you out, folks. I'm going to give you some exercises from section 2.6 to practice these skills. Make it a great day, and I'll talk to you soon.